Today we are playing around with electrons, playing around with Pell numbers, playing around with valid phone numbers, comprising numbers from digits, adding one to those numbers and then splitting them back into digits, and then we are finding the first non-repeating character in a string regardless of case. Hello world, and this is versus Codewars. We begin today with the warm-up segment, a series of easier katas in order to prepare for the more difficult katas later in the episode, starting with a conversion from DNA to RNA. Deoxyribonucleic acid, or DNA, is the primary information storage molecule in biological systems. It is composed of 4 nucleic acid bases, guanine, cytosine, adenine, and thymine. Ribonucleic acid, or RNA, is the primary messenger molecule in cells. RNA differs slightly from DNA in that its chemical structure contains no thymine. In RNA, thymine is replaced by another nucleic acid known as uracil, or U. The goal of this kata is, given a DNA string, we are to convert it into an RNA string by taking all of the T's in the DNA string and replacing them with U's. Let's go ahead and give this a try here. And what we'll do is const DNA to RNA. We have our DNA as a string. We have our DNA string as an argument here. And what we'll go ahead and do is DNA.replace. We're going to use a little bit of a regular expression to pick up all of the U's in our T's rather in our string here. And we're going to replace them with U's. All right. Probably make a case insensitive too. Let's go ahead and punch this into Codewars and see what that looks like here. Run the tests. And we are good on that. Our next warm-up kata, we are calculating body mass index. The goal of this one is to write a function that calculates the BMI by calculating the weight divided by the height squared. If the BMI is less than 18.5, we return underweight. If the BMI is less than 25, less than or equal to rather 25, we return normal. If it's less than or equal to 30, we return overweight. And if it's greater than 30, then we return obese. Let's go ahead and give this one a try here. Const of BMI, we take a weight and a height. And what we'll go ahead and do, we're going to go ahead and make this calculation here. Const index equals, and it says here, weight divided by height to the power of 2. And what we'll do here is switch index, or rather, if index is less than or equal to 18.5, we return underweight. Else if index is less than or equal to 25, we return normal. Else if our index is less than 30, we return overweight. And otherwise, we return obese. Alright, let's go ahead and punch this into Codewars and see what this looks like here. And we are good on that. Our next warm-up kata, we are given an array of integers, and our goal is to find the maximum product obtained by multiplying 2 adjacent numbers in the array. Alright, let's go ahead and give this one a try. 2 adjacent numbers in the array. Const adjacent elements product. We have our array of integers here. Hold on. And what we'll go ahead and do is we're going to go ahead and iterate from 0 all the way until the length of our array minus 1. Alright, we're going to go ahead and keep track of a max product here. Let max product set that equal to minus 1 for now. This is going to be what's returned here. Alright, we're going to go ahead and in this for loop, we're going to calculate the integer at the current index times the integer at the next index. And we'll do that by doing this. Const product equals integers at I times integers at I plus 1. And if our product is greater than our max product, we will go ahead and reassign our max product right here. And we will go ahead and return that here. Let's go ahead and punch this into Codewars and see how that looks like. Alright, what's going on here? Alright, let's go ahead. Number.min safe integer. How about we try this constant here, the minimum safe integer. Try that one. And we are good on that. Our fourth warm-up kata, we are scaling squared strings. We are given a string of n lines, each substring being n characters long. For example, consider this new line separated string right here. Alright, we will study the horizontal and the vertical scaling of this square of strings. A k horizontal scaling of a string consists of replicating k times each character of the string, with the exception of the new line, as seen here. And a v vertical scaling of a string consists of replicating v times each part of the squared string, as seen here. And the goal of this kata is to write a function that will perform a k horizontal scaling and a v vertical scaling, as seen in this example right here. K and v will be positive integers. If the string is blank, we will return a blank string. Let's go ahead and give this a try here. Alright, const scale. We have our string, we have our k, our horizontal, and our vertical scaling here. And what we'll go ahead and do, now this string will be separated by new lines. So, what I imagine we'll be able to do is first we'll go ahead and break the string into its individual lines. Const lines equals string.split using a new line separator. Alright, we'll go ahead and iterate over each line here. And what I think I'll go ahead and try doing here is split each line further into its separate characters. Actually, what I think we'll do instead of this for loop here, for const let line of lines. We'll go ahead and split that line into its individual characters here. Const char equal line dot split with a blank string separator here. Now we will want to scale each of these characters by our horizontal scaling here. What I think I'll go ahead and do is let new line equals this, or rather scaled line equal this blank string here, or const char of our characters here. And what we'll go ahead and do is scaled line equals char.repeat HORZ. We'll pass in our HORZ that we passed into our Kata function right here. And once we're all done with that, we'll go ahead and replace our line with our scaled line here. Alright, next, what we'll go ahead and do, we'll do our vertical scaling next. Alright, we got our let line of lines here. I think we'll go ahead and keep track of a little bit of a counter here. And we'll loop our counter each time we, with each iteration of this for loop right here. And what we'll go ahead and do is we're going to go ahead and insert this scaled line. We're going to go ahead and set this actually to line here. And what we'll go ahead and do, we're going to go ahead and scale this line itself downwards by the number of times specified in our vert parameter right here. And we'll do that by doing this. For let I equals 0, I is less than vert plus plus I. And what we'll go ahead and do, we're going to try doing a no. Okay. Alright. Can't do it like that. Actually, what we'll need to do, we're going to go ahead and reiterate over our lines here. Alright, I might have to rethink this right here. Alright, we have our scale function here. It takes a string as a parameter, this first parameter, the horizontal scaling as the second one, and the vert scaling as the third one. Alright, what we'll need to do, we're going to go ahead and split these lines. Split this string into its individual lines by doing string.split with a new line separator here. Alright, I think what we'll go ahead and do is iterate over each. I think we'll set up actually a new array here. Scaled lines. We'll set that to a new array right here. We're going to go ahead and iterate over each of our lines here. Yeah, our scaled lines is going to be what's returned here. Return scaled lines.join with a new line separator here. Alright, for each line of our separated lines here, what we'll go ahead and do is, first we'll go ahead and scale the line itself over the horizontal parameter. We'll go ahead and let scaled line singular equal a blank string. We'll go ahead and iterate over each character of our line here. And what we'll do is scaled line plus equals char.repeat HORZ. Then what we'll go ahead and do from there for let for let I equals 0, I is less than vert plus plus I, scaled lines dot push our scaled line. Yeah, that ought to do it here. Let's go ahead and test this out here. Let's explain what's going on here. We have our Kata solution here. It takes a string as an argument, the horizontal scaling, and the vert scaling here. We take our string and separate it into its individual lines here using the split method and a new line separator. We keep track of an array called scaled lines, which will contain our string scaled horizontally and vertically. We iterate over each line of the substrings, or excuse me, we iterate over each of the substrings from the split here. We keep track of a string here called scale line. We set it to a blank string initially here. And then for each character of the current line here, we add that character repeated as many times as specified by the HORZ parameter stated right here. And then we loop from 0 to the number of times we want our vertical scaling to be passed in here. And for each time, we push that scaled line into our scaled lines array right here. Now, at the end of this outer loop here, we go ahead and join all of our scaled lines together with a new line separator. Alright, let's go ahead and test this out here. I've got this string right here. I'm going to do gunsel.log scale this string 2 times horizontally and 3 times vertically. Let's run this through Node and see what that looks like here. And as you can see, we have each of the characters of our line scaled horizontally twice, and each line scaled vertically 3 times. Alright, let's go ahead and punch this into Codewars and see what this looks like here. The tests. And we have a problem here. Oh, yes. If the string is blank, we just go ahead and return a blank string. Let's try that again here. And we are good on that. Finally, in our previous episode of Versus Codewars, we were dealing with a rule of divisibility by 13. Today, we are dealing with a rule of divisibility by 7. A number m of the form 10x plus y is divisible by 7 if and only if x minus 2y is divisible by 7. In other words, we subtract twice the last digit from the number formed by the remaining digits. We continue to do this until a number known to be divisible by 7 is obtained. You can stop when this number has at most 2 digits because you are supposed to know if a number has of at most 2 digits is divisible by 7 or not. The original number is divisible by 7 if and only if the last number obtained using this procedure is divisible by 7. For instance here, let's say m is 371. Alright, we take the first 2 digits of that, 37, and subtract 2 times the first digit, or 2 times 1. So we have 37 times 2 is 35. Since 35 is divisible by 7, 371 must be divisible by 7 as well. The goal of this kata is to return a pair of numbers, the first being the last number m with at most 2 digits obtained by the kata function. This last m will be divisible or not by 7. And the second one being the number of steps to get that result. Alright, let's go ahead and give this a try here. Alright, const 7, and we have our number here. Alright, we need to keep track of the number of times that we are doing this here. Alright, we're going to go ahead and keep track of a result. We're going to initially set that to our number here. While... And what we're going to go ahead and do here is... Alright, we need to Alright, we're supposed to stop when this number has at most 2 digits here. So, what we'll go ahead and do, we're going to come up with a little bit of a helper function here. We're going to call it getDigits. We're going to pass in a number here. And what we'll do with that function is we're going to return number.toString, split into its individual characters, .map char parse int char. So we have this helper function to extract the digits from a number here. And what we'll do here is let result digits equals get digits and pass in our result here. While result digits is greater than 2. And then what we'll go ahead and do here is result digits.length rather. Or what we'll go ahead and do is, we'll get to the, we'll create a number out of the all but the last digit here. And we'll do that by const all but last digit number. We'll set that to parse int. I think it is result digits to slice from 0 to -1 dot join with a blank string separator here. And then we'll go ahead and get the final digit just by doing result digits at result digits dot length -1. And what we'll go ahead and do is const, we'll do let result equal, I think it's all but last digit number minus final digit times 2 here. All right, now we'll increment our times here by the number of times we do this operation here. If result, the remainder of result divided by 7 is 0, we need to return a pair here. And that pair okay, yeah, what we'll go ahead and do at the end of this while loop here, we return in our pair our result and our times. And take our result digits here. All right, let's explain what's going on here. All right, we have our helper function called getDigits. It takes a number as a parameter. It takes our number, converts it into a string, splits it into its individual characters, and then maps each character out to its integer representation here, converts it into an integer here. Now for our main Kata solution here, we have our function here called 7. It takes a number as a parameter. We set our result to this number here, and we use the getDigits helper function to get its digits, storing it here in this array here. Now we keep track of the number of times we carry out this operation in our while loop here, which repeats as long as the length of our result digits array is greater than 2. Alright, we take all but the last digit of our number here, our result current number here, by running this result digits array through the slice method, starting at 0 and ending at just before the last element of that array here. And then we join that together with a blank string separator, and we use parseInt to convert that resulting string into a number here. And then we get the final digit here by indexing the last element of our result digits array here. Alright, we calculate a new result by taking the all but last digit number and subtracting twice our final digit right here. We update the result digits array by getting the digits of this new result. We then increment the amount of times we carry out this operation by 1. And this continues until the length of our result digits array is equal or less than 2. In which case, at the end of this loop, we return a pair with our result and the number of times we carry out this operation. Let's go ahead and test this out here. Console.log 7, and we pass in 371. I expect to see a pair of 35 and 1. Let's run this to the code and see what that looks like here. And we do receive a pair, 35 and 1. Let's try 1603. We receive 7 and 2. Let's try this big number here. I think that is 477,557,101. And we get a pair of 28 and 7. Alright, let's go ahead and punch this into Codewars and see what that looks like. Alright, run our test here. And we are good on that. That concludes today's warm-up segment. I will see you in the next kata. Today we are a mad scientist, and we've decided to play with electron distribution among an atom's shells. The basic idea of electron distribution is that the electrons should fill a shell until it's holding the maximum number of electrons. Given an integer representing the number of electrons, the goal of this kata is to distribute those electrons such that they fill shells until they hold a maximum number of electrons. This maximum number is 2n to the power of 2, where n is the position of the shell. Electrons should fill the lowest shell first. This function will return an array representing the number of electrons filling each shell. Let's go ahead and give this a try here. Alright, we'll go ahead and keep track of a result here. And this is what will be returned. Alright, go ahead and let electrons left equal electron count. Shell, keep track of the shell position as well here. And we'll do while electrons left is greater than 0 here. And let electrons in shell equals 0. Electrons in shell plus plus in this while loop here. And if electrons in shell is equal to 2 to the power of shell position, or rather 2 times shell position to the power of 2, then we'll increment shell position, reset our electrons in shell to 0. Alright, we're going to go ahead and push our current electrons in shell value into the results array. Alright, let's explain what's going on here. We have our kata function, atomic number. It takes our electron count as a lone parameter here. We keep track of an array here, which represents the number of electrons in each shell once they're all distributed here. Alright, we keep track of how many electrons we have left to distribute. We keep track of the current number of electrons in the current shell, and we keep track of the current shell position, which we start at 1. In this while loop, which loops until electrons left is equal to 0, we increment our electrons in shell value here, and we will also go ahead and do electrons left minus minus. We decrement the number of electrons remaining here. And we do this check here. If the current electrons in our current shell is equal to the maximum amount of electrons allowed in that shell, which, recall, is 2n to the power of 2. 2 times the shell position to the power of 2. We then go ahead and push our electrons and shell value into our results array. We increment our shell position, and then we reset our electrons and shell count here. Now, at the end of this while loop, we go ahead and return our results array here. Let's go ahead and test this out here. Let's try console.log atomic number. Let's pass in 61. Alright, let's punch this in a node and see what that looks like here. We have 4, 16, and 36, and that is actually not what we want. Alright, this was 2n to the power of 2, correct? Unless shell position has to start as 0. No. Okay, it has to start at 1. When we get our 4, 16, and 36, and that is not what we're looking for. 2 times 0 is 0. 0 to the power of 2 is should be 0. Okay, let's have a look at this here. 2, 8, 18. 2 to the power of 1 is 2. 2 times 1 is 2. 2 to the power of 2 is 4. 2 times 0 is 0. 0 to the power of 2 is 0. 2 times 1 is 2, unless... What if we did 1 to the power of 2 first? And we still have 4. 1 to the power of 2 would be 1. 1 times 2 is 2. Okay. I think we got our math wrong here. 2 times shell position to the power of 2. Yep, and we have our 2, 8, 18, and 32. And that is the result we are looking for here. We passed in 61 here. And we have an electron missing here. Okay, what we'll go ahead and do after that, after our while loop, is if electrons in shell is greater than 0, then result.push electrons in shell. Let's try that. Yep, and we do have our 1 at the end here. Let's go ahead and punch this into Codewars and see what this looks like here. We're going to test. And we are good. The thing that was tripping me up in this Kata solution was, when I read 2n to the power of 2 in the Kata instructions, I was reading that equation from left to right, and forgetting to apply the order of operations. First take n and raise it to the power of 2, and then multiply that result by 2 to get the proper maximum number of electrons in the shell at the current position. The Pell sequence is a sequence of integers such that the first element is 0, the second element is 1, and element n is equal to 2 times the element before it plus the element 2 places before n. Given an integer n, the goal of this kata is to return the nth number in the Pell sequence. Let's go ahead and give this one a try here. We're going to be using a little bit of recursion here. First, we need to check if n is equal to 0. Then we return 0. Now, is this base 0 or base 1? Yeah, this is probably going to be base 0 here. Yep. Else, if n is equal to 1, we return 1. Otherwise, we go ahead and return 2 times Pell. We pass in n minus 1 plus Pell. Pass in n minus 2. Alright. Fairly straightforward. We're using a little bit of recursion to calculate the elements of the Pell sequence 1 place and 2 places before n here. And we're adding those together and multiplying that by 2. Alright, what we'll go ahead and do here is we're going to go ahead and test this out here. Console.log. We're going to pass in our Pell. Just pass in 4. I expect to see 12 here. Let's feed this in a node here. And we do, in fact, see 12. Let's pass in a big number here. About 10,000. See how long that takes to clear here. Eight, 9, 10, 11, 12. That could cause problems here. I imagine we'll see a timeout here. Let's punch this into Codewars and see if we do see a timeout here. And sure enough, I do believe we have a timeout here. Okay. So it looks like recursion's not going to do it here. Alright, let's console.log our n and see what that looks like here.
Yeah, that doesn't work either. Yeah, maybe that's not the best way to go here. Alright, let's go ahead and
actually log out the numbers of our Pell sequence here. Alright, I'm going to go ahead and comment this out here. We're going to keep an array. We want to go ahead and keep an array here. Const terms. We'll set that equal to 0 and 1. For while terms.length is less than n, and we'll do terms.push two times terms at terms.length minus 1 plus terms at terms.length minus 2. Let's play with that a little bit here. We get undefined here. That's an encouraging sign here. Alright, let's go ahead and return terms at terms.length minus 1. Turn that last term here, infinity. Alright, how about 100 here? How about that fourth term that we had back before? That's actually the third term here. To receive 12. Revisit that 10,000 here. Infinity, so we know at least it's resolving here. Let's go ahead and feed this into Codewars and see what that portends here. Run the tests. Let's hit attempt. And we have a problem. At least we're not timing out, though. Oh. Okay, looks... Uh-oh, looks like we are dealing with big integers here. Okay, what we'll try doing here. Try passing in a big int here. And let's try passing in 100 here. Yep, I think that is what they were looking for here. Alright. Big int. Yeah, let's go ahead and reflect that in our Kata solution in here. Encapsulate this number inside of a big int constructor here. Still problems. Okay. Alright, we're going to go ahead and console.log that here. In our local solution here. Console.log big int terms at terms.length -1. Alright, we're going to go ahead and run that through our local solution here. And what we'll go ahead and do is terms.length. We're going to go ahead and examine this here.
2, 5, 12, 29, 71, 79. I'm going to handle the multiplication first. What if we encapsulated this in parentheses here? That area. Alright, let's pass in 170 here. 417, 178, 811, 644, 252, 907. Ah.
This is merely an approximation here. Let's look at the Kata instructions again. Just to see where are we going wrong here. You know what? I think I know. Let's get rid of that -1 here and number NaN cannot be.
Oh, right. Yeah, we're getting the last two all into our array. Pn -1, Pn -2. I assume order of operations is a matter here. Let's go ahead and get rid of this console.log here. And we'll go ahead and console.log our terms array here.
Oh, wait a minute. Alright, I think I know where I'm going wrong here. Maybe we need to create the big int out of that number here before we push it into the array. Alright, and then we'll go ahead and make big ints out of our 0 and 1 here. Cannot mix big int and other types. Use explicit conversions. Alright, I think this is more or less the output they were looking for here. 529 621 346 430. I think I got it here. Let's go ahead and get rid of this comment line here. And what we'll go ahead and do, we're going to go ahead and punch this into Codewars instead. Try running the tests. And we are good. I'd like to introduce you to big ints. In this Kata solution, you saw an introduction to the big int primitive in JavaScript, which is basically a very large integer. You can declare a big int using the big int constructor, as you saw in this Kata solution, or you can append the lowercase n to a very long integer literal. Big ints can be used in mathematical operations with other big ints, but they cannot be mixed with other regular numbers unless those regular numbers are coerced into big ints. Also, big ints are not supported by the methods in the math object. For more information on big int, there is a link in the description to its article on MDN. Given a string, the goal of this kata is to check to see if that string is a valid phone number. We're going to be using regular expressions for this one. And the regular expression we're going to be using is const phone regex. Alright, our number is going to be of the format. Alright, we're going to start. Our number is going to be of the format. Opening parentheses, number, closing parentheses, space, number, dash, number. So what we're going to go ahead and do, we have our regular expression here. We're going to have our start of our string here, our opening parentheses. I think the character class for numbers is capital D. Do correct me if I'm wrong here. Alright, we have for D3 and our dash. And then our D4 here. And then we will return true if phone regex.test on our phone number returns true. Alright, let's go ahead and give this a little test run here. Console.log valid phone number. We have our 12345678990. Let's feed this in a node and see what this looks like here. And this returns false. So this is probably supposed to be a lowercase d then. Yep. This returns true. Get rid of the dash here. This returns false. And actually we need to go ahead and put this at the end of the string here to indicate the end of the string in our regular expression. Alright, let's go ahead and punch this into Codewars and see what this looks like. To attempt. And we are good. I don't have anything to say about this one, but here is a lesson in character classes and regular expressions. The /d character class, the /d character class, is used to look for numbers in regular expressions. Use capital D instead if you want to look for anything that's not a number in your regular expression. Use the /w to look for words, letters in your regular expressions. Use /W to look for anything that is not a letter in your regular expression. Finally, use /s to look for white spaces in your regular expression, and use /S to look for anything that is not a white space in your regular expression. Given an array of single-digit integers, the goal of this kata is to return, in an array, the digits of the number comprised of the given digits plus 1. Now, the array cannot be empty, and only non-negative single-digit integers are allowed. We have to return null for invalid inputs. Let's go ahead and get started here. First, we need to check to see if our array is empty here. Digits.length is equal to 0. We return null. Next, we need to see if our array here has negative numbers, or numbers that are not single digit. And when we do that by checking to see if this array is invalid, const is invalid, we'll take the digits and run it by the sum method. And in the predicate function, we have our digit, and we return true if digit is less than 0 or digit is greater than 9. That way we know that the digit is either negative, or the number is either negative or multiple digits, in which case, if is invalid is equal to true, we return null. Alright, now that the checks are out of the way, let's get to the meat and potatoes of this kata solution here. And we will do that by doing this. We will return the following. We'll take the digits. Alright, we're going to go ahead and run through the parse int method here, function here, and in this function we will pass in our digits joined together by a blank string. And we are going to go ahead, actually, what we're going to go ahead and do, const added, and what we're going to go ahead and do, we're going to use the parse int method here, and we're going to pass into it the digits joined together into a string with a blank string separator here, and we're going to add 1 to that. And then we're going to go ahead and do added dot toString dot split into its individual characters dot map char parse int char. So let's explain what's going on here. We have our function upArray, and we have our array of digits. We do some checks here before we get to the body of the kata solution. We return null if one of the following is true. The length of the digits array is 0. In other words, we're dealing with an empty array. Or the digits array is invalid. A digits array is invalid if one or more of the digits therein are less than 0, or greater than 9, in which case we return null as well. Next, we take the digits, join them together with a blank string separator, parse it out as an integer, and then add 1 to that returned integer. We take that resulting integer, convert it into a string, split it into its individual characters, and then map each character out to an integer to get their digits here. And this digits array is what is returned. Let's go ahead and test this out here. Console.log up array. Let's pass in 2, 3, and 9, just like we have in our kata solution here. Whoops. That's not what we want. Whoops. Let's add this, punch this into Node and see what that looks like. And we have our array of digits 2, 4, and 0. Let's try another one here. 4, 3, 2, and 5. And we have 4, 2, 3, and 6 now. Let's try some invalid arrays here. Empty array returns null. 1 minus 2, 4. Should also return null. 1, 22, and 4 should also return null because 22 is a multiple digit number here. Alright, let's go ahead and punch this into Codewars and see what this looks like. And we have a problem. Alright, what is... big arrays. Okay. I think it's time we brought back that big int constructor again. Alright, let's go ahead and... bring this gigantic array of numbers in here. Let's go ahead and test this one out here. Cannot mix... Okay, what we need... Alright. I think we got that squared away here. What we did here instead of using parse int here, I went ahead and used the big int constructor again here, and then I appended the lowercase n to this one here to make this a big int as well. Let's go ahead and punch this into Codewars now and see what this looks like. Run the initial test here and... invalid or unexpected token. Okay.
Let's go ahead and console.log that here. Okay. Because and equals big and digits not join. Alright, let's see what we have in our test here. No, isn't that just the strangest thing? An invalid or unexpected token.
Okay, let's go ahead and revisit some of our smaller tests here. Our 2, 3, and 9. We have our 2, 4, and 0. Okay, let's run this. Let's do 1 minus 9 here. We have our null. So what appears to be the problem here? 4, 2, 3, and 9. 4, 2, 4, and 0. Okay, let's copy this in here. Alright, what appears to be the problem here? Alright, I'm going to go ahead and console.log our digits in here. Yeah, I'm going to change the node version here. Try this so that... Okay. So it seems changing the node version in this Kata instructions here seems to work. Alright, let's go ahead and attempt this one here, and we are good. Once again, big int saved the day. The issue I had with this Kata solution, particularly with the tests, were that the Kata tests were running on Node.js version 8.1.3. That particular version of Node did not have support for JavaScript's big int primitive. By setting the Node version for the test up to Node.js version 10.x, I was able to get the big ints working and the test passing. Node.js version 10.4 added support for JavaScript's big int primitive. Given a string, the goal of this kata is to return the first character of that string that occurs only once, regardless of case. As an added challenge, upper and lower case letters are considered the same character, but the function should return the correct case for that initial letter. The character return has to have case preserved. If a string contains all repeating characters, it should return an empty string. Let's go ahead and get started with this here. First, we need to find the index of the character that occurs only once in the string. First, let's go ahead and do that here. Const non-repeating index. And what we'll do is take the string, convert it to lowercase, and then I think what we'll go ahead and do, we'll split that into its individual characters with a blank string separator, and then we'll run that array through find index. Alright, this takes a predicate function for an argument here, and returns the index of the element in the array for which this predicate function returns true. So what we'll go ahead and do, we'll pass in our char here, and what we'll do is we will need the array here. What we'll do is array.index of char is equal to arr.last index of char. Alright, what we'll do now, if this non-repeating index here is equal to -1, we will return a blank string. Now, what we'll go ahead and do, it can be safely assumed that this resulting array here will have the same number of elements as this string here has characters. So what we can do, we'll return str at non-repeating index. Alright, let's explain what's going on here. First, we have this Kata function, first non-repeating letter, and it takes a string as an argument here. We first look for the index of the character, regardless of case, in the string that occurs only once, the first character thereof. And we do that by taking the string, converting it into lowercase first, because initially we're ignoring casing here. We split that string into its individual characters with the blank string separator. Then we run that resulting array through the find index method. Now the predicate function passed into find index takes 3 arguments. The character being worked on, the index of that character in the array, which we are not using here, hence the underscore, and then the array itself being worked on. We return true if the return values of arr.indexOf and arr.lastIndexOf, passing the character into each method, returns the same value. And if it does, the index of that character will be returned by find index. However, if this returns -1, then we know this string consists entirely of repeating characters, so we return a blank string. Now, because we know the character return must have the case preserved from this original string here, we tap into this original string here, and we get the character at the index that was returned here. Alright, let's go ahead and test this out here. Let's explore some test cases here. Console.log. First, non-repeating letter. Let's pass in M-O-N, Moonmen. Moonmen. Alright, let's feed that in the node and see what that looks like here. No non-repeat char, and we do see the letter E as our return here, which is what we want. Alright, let's go ahead and pass this into Codewars and see what this looks like here. And we are good. Here is the clever code solution of the day. Pay mind to the code snippet you see below me here. Here we iterate over every character in the string that we pass in. And then for every character we run the string through its match method. The string object's match method takes 1 parameter, which is a regular expression. Here, a new regular expression is created with the regular expression constructor. That constructor takes 2 arguments. A string representing what we want to look for in this regular expression in our string, and then the regular expression's flags. In this case, the string we want to look for is the current character. And in the flags, we want to tell the regular expression to look for all matches of that character with the G flag and ignore case with the I flag. Now the match method will return an array with all of the matches that regular expression turns up. We want to check that array's length, and if that length is equal to 1, we return that character. If we reach the end of the loop without turning up a match, we return a blank string. And that will do it for today's episode of Versus Codewars. If you like this video or you learned something new, drop a like and subscribe to this channel to see me take on more coding challenges on Codewars. As always, if you think there's anything I can do to improve on my code for the better, feel free to drop a suggestion in the comments section below. I hope you have a wonderful day, and I will see you on the next episode of Versus Codewars.